So everyone, I found some resource we can use to start Xv6 learning, and this is the website from the um, MIT Operating System Engineering course that we can take a look and really delve into the part of operating system we need to get into. Let's look at the setup. For this class, we'll need the risk-free versions of QEMU, GDB, GCC, and binutils. If you're having trouble getting things set up, please come to office hours or Piazza. We're happy to help. sudo apt-get install git build essential GDB multi-arch QEMU system miscellaneous. Okay. I think I have most of it, but let's just to make sure we have everything to download it. Uh, yes, install it. You likely need to be running Ubuntu 24 in order for apt-get to install a recent enough QEMU. Alright, so that part is done. Linux, let's zoom it up a bit. Running a Linux VM. If you're running an operating system which it's not convenient to install the risk-free tools, well, it doesn't apply to me. I already downloaded. Okay. And then Dina, testing your installation. Okay, let's test it. Test the operating motherfucker. Okay. Emulator 8.2.2. Okay, I have it. Where this one is a version of GCC cross compiler. Okay, I have it. And then here I have it again. Oh, not found, but at least one is QV version. I have the known version, Linux version, so gonna be okay. But just checking for fun. Okay, not found. It's okay. Alright, so I have the tools. Then go to guidance. What? Chapter, addressing modes, PDP 11. I think this is a very old one. Nah, I'm not sure really. Uh, let's, let's see if we can avoid it. But let's just read this first. Hardness of assignments. Okay, something easy, moderate, hard. This time, sorry, rough estimates of our expectations. Debugging tips. Here's some tips for debugging. Okay, fuck you. Let's go to the next one. Why so slow all of a sudden? I can't stand it. Alright, let's Xv6 and Unix utilities. This lab will familiarize you with Xv6 and its system calls. Have a look at the lab tools page for information about how to set up your computer to run these labs. Oh, this was done. Okay, fetch the Git repository for the Xv6 source for the lab. Okay. And then go to this. Okay. The files you will need for this and subsequent labs are distributed using the Git version control system. For each of the labs, you will check out a version of Xv6 tailored for that lab. To learn more about Git, take a look at the Git user's manual, CS-oriented overview of Git. Git allows you to keep track of the changes for this, and subsequent labs are distributed the matter. Okay. I'm not interested in Git for now. You can view your changes with Git diff. Okay, whatever. Build and run Xv6. Okay, let's do this. Make Chimu. Yes, Chimu, let's do this. Ooh, let's see. Wow. Crazy, crazy running. Okay. Alright, if you type ls at the prompt, you should see output similar to the following. Okay, let's see. Find test Xv6 there's some more for sure. These are the files that make FS include the initial file system. Most are programs you can run. You just ran one of them, ls. Oh, what? Oh, I'm inside Chimu already. Okay. So this command line is itself from the this program. That's so cool. These are the files that make file. Okay. Xv6 has no ps command, but if you type Control P, the kernel will print information about each process. Okay, let's see if I can type P, Control P. Oh. Oh, okay. If you try it now, you'll see two lines, one for init and one for she. Okay, to quick keyboard type, Control. To quick keyboard, Control A followed by X. Well, it's not working. It's not working, sir. Shit. This exercise makes you familiar with writing a user program on Xv6 and the pause system call. Implement a user-level sleep program for Xv6 along the lines of the Unix sleep command. Your sleep should pause for user-specified number of ticks. A tick is a notion of time defined by the Xv6 kernel, namely the time between two interrupts from the timer chip. Your solution should be in the file user slash sleep.c. Well, why can I quit Chimu here? Enter. Oh, okay. Exec failed? What the fuck? Why the fuck did it fail? Uh, okay. Let's go to this. Why did I fail? Interesting. This is not what the instruction expected. Kimu exec failed. Control plus A followed by X. Using no graphics, press Control A, release, then press. Oh, okay. So this is the. You have to press Control A, and then release both keys, then press X. Ah, shit. Okay. Thank you. Thank you, I. Thank you, AI. This is so good these days. All right. Where was I? Okay. Now we are exited. So sleep. This exercise makes you familiar with writing a user program on Xv6 and pause system call. Some hints. Before you start coding, read chapter 1 of Xv6 book. Okay, let's do that. They love us to read books. These motherfuckers. Okay, I'm not gonna call them motherfuckers. They are respectful enough to have changed the world with the operating system that they're writing and educating people of it. That should be enough to earn every respect from everyone in the world, right? Okay, I think this book was something I read starting. Yeah, I read this book. Yeah. It's the one we have quit reading. Okay, so let's pick up from where we left then. Okay. Um, IO and file descriptors. A file descriptor is a small integer representing a kernel managed object that a process may read from or write to. A process may obtain a file descriptor by opening a file, directory, or device, or by creating a pipe, or by duplicating an existing descriptor. For simplicity, we'll often refer to the object of file descriptor refers to as a file. The file descriptor interface abstracts away the differences between files, pipes, and devices, making them all look like streams of bytes. We refer to input and output as I/O. Internally, the Xv6 kernel uses the file descriptor as an index into a per process table so that every process has a private space of file descriptors starting at 0. By convention, a process reads from file descriptor 0, writes output to file descriptor 1, and writes error messages to file descriptor 2. As we will see, the shell exploits the convention to implement I/O redirection and pipelines. The shell ensures that it always has 3 file descriptors open, which are by default file descriptors for the console. The read and write system calls read bytes from and write bytes to open files named by file descriptors. The call read reads at most n bytes from the file descriptor fd, copies them into buffer, and returns the number of bytes read. Each file descriptor that refers to a file has an offset associated with it. Reads data from the current file offset and then advances to that offset by the number of bytes read. A subsequent read will return the bytes following the ones returned by the first read. When there are no more bytes to read, read returns 0 to indicate the end of the file. The call write writes the n bytes from buffer to the file descriptor fd and returns the number of bytes written. Fewer than n bytes are written only when an error occurs. Like read write writes data writes data at the current file offset and then advances that offset by the number of bytes written. Each write picks up where the previous one left off. The following program fragment copies data from its standard input to its standard output. If an error occurs, it writes a message to the standard error. Curve buffer, int, read, write, whatever. Alright. The important thing to note in the code fragment is that cat doesn't know whether it is reading from a file, console, or a pipe. Similarly, cat doesn't know whether it is printing to a console or file or whatever. The use of file descriptors and the convention that file descriptor 0 is input and file descriptor 1 is output allows a simple implementation of cat. The closed system call releases a file descriptor, making it free for reuse by a future open, pipe, or dub system call. Newly allocated file descriptors always the lowest numbered unused descriptor of the current process. File descriptors and fork interact to make IO redirection easy to implement. Fork copies the parent file descriptor table along with its memory so that the child starts with exactly the same open files as the parent. The system call exec replaces the calling process's memory but preserves its file table. This behavior allows the shell to implement IO redirection by forking, closing, and reopening chosen file descriptors in the child, and then calling exec to run the new program. Here's a simplified version of the code a shell runs for the command cat less than input.text. After the child closes file descriptor 0, open is guaranteed to use the file descriptor for the newly opened input text. And 0 will be the smallest. So here we're defining what the cat command does. That's very interesting. The parent process's file descriptors are not changed by this sequence, since it modifies only the child's descriptors. The code for I/O redirection in the Xv6 shell works in exactly this way. Recall that at this point in the code, the shell has already forked the child shell, and that run command will call exec to load the new program. The second argument to open consists of a set of flags expressed as bits to control what open does. The possible values are defined in the file control header, or read only, or write only, or read write, or create or truncate, which instruct open to open the file for reading or for writing, or both reading and writing to create the file if it doesn't exist, and to truncate the file to 0 length. Alright, I think this is the time to stop. Rewrite some of the things that what we're doing. I'm currently doing the lab from the operating system engineering course, which does work on the risk-free system, Xv6 risk-free system. So I'm trying to learn basically how whatever the lean operating system looks like, and how we can actually create one operating system from scratch. Maybe it's not creating operating system from scratch, but learning the gist of what lean operating system does. And by looking at the chapter 1, as it recommended from this lab exercise, is that we're kind of defining what command line uh, interface, how command line how each command in the terminal, like open, read, write, can be defined, so we can write a code for those. Okay, so see you next time. Bye bye.